Hello everyone. In this video, we are going to talk about timestamp ordering algorithm. Now, timestamp ordering algorithm is also a concurrency control technique which can ensure conflict serializability, right? But in contrast to two-phase locking, timestamp ordering or TSO for short does not use locks. It rather uses timestamps to check for conflicts and all that, right? So in TSO algorithm, what we have is that every transaction which comes into the system is issued an timestamp. Okay, as you can guess, the timestamp of an old transaction will always be less than the timestamp of a new transaction, right? So that's how it goes. And now the TSO algorithm, it manages the concurrent execution such that the resulting schedule which gets formed in TSO algorithm, that is conflict equivalent to a serial schedule where transactions are executed in their increasing order of timestamp, right? Remember that it is still ensuring conflict serializability only, but all I'm saying is that the resulting schedule from TSO algorithm will be conflict equivalent to a serial schedule where transactions have been executed in according to their timestamp. That means older transaction was executed in that hypothetical serial schedule. The older transaction would have executed first and then the newer ones and so on, right? So this TSO algorithm output will be conflict equivalent to that serial schedule. Now let's see how TSO algorithm achieves that. Okay, so in order to achieve the goals of conflict serializability, TSO algorithm maintains some data structures, right? So for every data item queue which is there in your system, we will maintain two timestamps. So one is called as the write timestamp, the other one is called as the read timestamp. So write timestamp of any data item q is the largest timestamp of any transaction that has executed write q successfully, right? And likewise, read timestamp is the largest timestamp of any transaction that has executed read operation successfully. Okay, so whenever any transaction executes read or write, these values will get changed. Okay, now let's see how the TSO algorithm actually works, right? So the way TSO algorithm ensures conflict serializability is that let's say there are multiple transactions and they all are sort of getting executed in an interleaved fashion. Maybe because the CPU scheduler it's running some kind of a round robin where few instructions from every transaction are being executed. And let's say something like that is happening. Now, what TSO algorithm does is that it checks. So let's say that a transaction TI at some point in time it issues an read operation on data item Q. So at that stage, your TSO algorithm will will make some checks. We will talk about what those checks are, and only if those checks are passed, the TSO algorithm would allow for this read operation to proceed. Otherwise, TI will be rolled back, right? So that's how it goes. So it's more of an you can say that it's an lazy check strategy where things are just allowed to proceed, and just before a read or a write operation from any transaction, we check whether we should allow this read or not, right? So if the TSO algorithm is convinced that by allowing a particular read operation, that will violate my conflict serializability constraints, then the transaction is rolled back, right? So let's try to see what checks does TSO algorithm do, right? So suppose there is one transaction TI, and at some point in time, it issues an read request on a data item Q, right? So at that stage, we will check the write timestamp of Q, right? And let's see how that is done. If the timestamp of the transaction Ti, if that timestamp happens to be strictly less than the timestamp, the current write timestamp of Q, right? So then this operation is rejected, right? And you don't have to mug this up. There is a proper logic behind these statements, right? So let's closely watch what it is happening. So according to this statement, I'm saying that the timestamp of transaction Ti is less than the current write timestamp of Q. Now, when will that happen? That will happen when there was some transaction Tj, and that transaction Tj was younger than transaction Ti, and that younger transaction wrote on this data item Q, right? Whereas, as per our goals of TSO algorithm, which ensures conflict serializability in an order where where older transactions finish first and then the younger transactions, in that scheme of things, if you interpret this statement, what is happening? An older transaction Ti was supposed to perform the read operation on Q before an younger transaction. This read operation should have happened before a younger transaction came and wrote on Q, right? So that is the serializability order which we are going, right? So in this case, what is happening is that an older transaction is attempting to read Q, whereas a younger transaction has already written on it. So this read operation cannot be allowed, right? And therefore, Ti is rolled back. Now let's see the second case here. If transaction Ti, if timestamp of Ti, which is requesting this read operation, if that timestamp is greater than the current write timestamp of Q, so then what happens? So the meaning of this is older transactions have already written on Q, not a problem, and then a younger transaction is sort of trying to read it. This is allowed because as per our serializability order of older transactions finishing first and then the younger transactions executing, in that grand scheme of things, this is not a showstopper. Older ones finished whatever they wanted to do with Q, and now the younger one is trying to do a read operation. So this is allowed. Whereas over here, what has happened is that the older transaction was supposed to read before, but that did not happen because of some scheduling conflicts or some IO, something happened, and then the older transaction could not do the read before a younger transaction came and made some change, right? So that is why this was not allowed, whereas this is allowed. And when this read operation is executed, as I said before, the read timestamp of Q is set to the max of the current read timestamp and the timestamp of Ti. Right? I think this is self-explanatory what is happening. Right? So these are the checks which are made whenever a transaction Ti issues an read operation. Now let us see what happens when we issue a write operation, right? So just see this here. So over in this case, a transaction Ti is requesting for a write operation on data item Q, right? Now let's see what does these conditions mean over here. So in the first case, I'm checking if the timestamp of Ti is less than the current read timestamp of Q, right? So in this case, I'm saying that the write operation must be rejected. And why is that so? Because in our grand scheme of things, if this is true, then Ti is an older transaction, and it was supposed to write onto this data item Q, which a younger transaction should have read it, right? But now what has happened is that, if this if condition is true, then what is happening over here is that the younger transaction has already gone ahead and read the data item q, right? Only in that case the read timestamp of q will be greater than the timestamp of ti, right? So this is not correct, because in our grand scheme, where we are trying to achieve the serializability order in terms of timestamps, ti, being an older transaction, should have finished its write operation before a younger transaction performed the read, right? But that did not happen, maybe because of various other reasons, right? So now, if we allow ti to do the write, then our serializability order is broken. So therefore this operation has to be rejected under this condition, right? So let's say this passes, and now then we'll check the second one. So in the second one, I am checking whether if the timestamp of ti is less than the write timestamp of q, right? If that is the case, then again the write operation is rejected. Why is that? Because if this is true, then a younger transaction has already written on data item q, right? And now ti, if you allow ti to write, you are sort of writing an obsolete value of q, right? Because in the I'll keep going back to my example of achieving serializability order in terms of timestamps, right? So wherein older transactions should finish their jobs first, and then the younger transactions should do their jobs, right? But if this is true, then what has happened is that a younger transaction has sort of beaten ti to writing q, right? So therefore we cannot allow write operation under this case also, right? In both these cases, ti will be simply rolled back. Now, if both these cases are not valid for this write operation, then the write operation is executed, and then you update the write timestamp also. Okay. Now for the TSO algorithm, you can expect questions like this, wherein I'll give you some transactions ti and t2, t1 and t2, and then I'll give you the timestamps of t1 and t2. In this case, timestamp of t1 is 3, and timestamp of t2 is equal to 1, right? And then let's say I'll give you an hypothetical interleaving, and then my question would be that you check all these operations against the policies of TSO algorithm, and then tell me whether these read requests and write requests will be allowed or not. Okay, so you have to check every time here, right? So you'll have to maintain the write timestamp and the read timestamp of this x and y, and then for every read operation and write operation, you have to check whether they follow according to the TSO policies or not. If they follow, then fine, you go forward. If at any one place, if you see that they are not followed, you have to mark that, okay, this particular operation is not allowed because of this case, and then hence the transaction is sort of rolled back, right? So you have to write an answer like this, right? So as an exercise, I think you should apply the TSO policies onto this schedule and tell me which of these operations are allowed and which are not allowed. And if you have any doubts, you should get back to me. Okay, one small thing. So here I have said that TI is rolled whenever these checks fail. So TI is rolled back, and then you restart the transaction. So when you are restarting the transaction, make sure that we make sure that that TI starts with an younger value of the timestamp. Otherwise, if you restart the transaction with the old value of the timestamp only, then it will not be correct semantically. And even it will even create trouble with the checks also, right? Here you will again things will again get rejected, right? So whenever you are restarting this TI after rolling back, it has to start with an younger value of timestamp, or the larger value of timestamp would be given to TI. Okay. Okay, so now I wanted to take few slides to discuss about the recoverability and cascadeless nature of the TSO algorithm, because TSO algorithm by itself will ensure conflict serializability, but as we always say, that is not sufficient. We also need some guarantees on recoverability and preferably cascadeless recoverability. Okay, so it so turns out that TSO algorithm is prone to having trouble with recovery, right? So here is an example on that. So let's say there is some transaction TI which aborts because of a failure of passing some checks in as per the TSO, but then it so happens that TJ has already read a data item which was read by TI. So this is a dirty read problem. And moreover, if TJ is allowed to commit, uh, right, then what has happened is that not only you have done dirty read from a transaction which has aborted, you have also gone ahead and committed the TJ. So that is like the absolute blasphemy in terms of recoverability, right? So TJ should not have been allowed to commit, because if TJ commits after doing a dirty read, and the older transaction aborts, then this schedule is not even recoverable, right? So as I keep saying, so you would be uh, here it's like canceling a ticket after the ticket has been issued, right? Okay, so these problems exist. TSO by itself does not guarantee recoverability, and also, of course, if recoverability is not guaranteed, then cascading rollback is anyways an issue, right? So there are some fixes which can be done to TSO algorithm to get recoverability and cascadeless, and they all involve some kind of extra checks, right? So for example, one solution is to actually keep a note of from where all transaction has read values, so that before committing you can check that if you have consumed the output from some other transactions, then make sure that at least before committing you check whether the others have committed or not. Okay, so those kind of things, modifications have been done to TSO. Okay, when your textbook gives a few more solutions, but I'll leave it to you to read that. Okay, now there is an modified version of the TSO algorithm, which is slightly better in giving more concurrency, right? So this is called as TSO algorithm with Thomas Wright rule, right? So it's essentially the same TSO algorithm, but with one small change. You may recall that in TSO algorithm, when whenever a TI attempts to write on a data item Q, we do perform this check that if timestamp of TI was less than the current write timestamp of Q, then we used to reject TI's operation, and we used to even roll back TI. Why? Because here the right timestamp, here the timestamp of ti is less than the right timestamp, current right timestamp of q. That means an older transaction, that transaction ti was supposed to write on data item q before a younger transaction comes in and write on q, because that's our grand goal of achieving serializability in TSO, right? So if we had allowed TI to write, then it was kind of performing an obsolete write operation, right? So in in under Thomas Wright rule, what we do is that instead of rejecting this write operation, only in this case, we will instead of rejecting, we will just ignore this write operation, ignore the write operation, right? Otherwise the protocol is the same as TSO, right? So just to go back to those old slides, uh, TSO algorithm with Thomas Wright rule will have the same policy for the read operation, and for the write operation under Thomas Wright rule, this check will not be done, or rather, the way I should say is that instead of not done, I should say that, if this is happening, this check goes to true under Thomas Wright rule, instead of rejecting Ti and, rolling back, we will, just ignore this write operation. Right? So this is different from rolling back Ti. This is just rejection of operation. Right? So rest everything is same as TSO. And now when you are sort of relaxing this condition under Thomas Wright rule, what happens is that, this protocol will can, no longer guarantee conflict serializability. Right? So TSO algorithm under Thomas Wright rule, it generates something called as view serializable schedules. Right? They have slightly better concurrency, but, they are certainly not conflict serializable. Now let's see what are these view serializable schedules. I think I have some examples here. Right? So by definition, a view serializable schedule is a schedule which is view equivalent to a serial schedule. Now let us see what is view equivalent. Okay, so let's say that there are two schedules, S and S prime, and, and both these schedules, they have the same set of transactions. Then we will say that S and S prime are view equivalent to each other if the following conditions are met for every data item Q which is being touched. Right? And what are those conditions? Right? So the first condition is that, if a transaction Ti reads the initial value of Q in schedule S, then the transaction Ti must also read the initial value of Q in S prime. Right? So in other words, if Ti reads the initial value of Q in S, then in S prime also Ti should read the initial value of Q. Right? So the starting point, whosoever touches this Q first should be same in both S and S prime. Right? That's what this means. And the second point being, if a transaction Tk, there is some transaction Tk, right? If it is consuming the output of a transaction Tj, right? That means, Tk is doing a read queue operation, and that read queue is sort of consuming the write queue output of some transaction Tj. Then, this ordering of read and write should be maintained in both S and S prime. Right? So this is the second condition. So the first condition was that, the initial value should be same, or the transaction which is reading the initial value should be the same. And second condition says that, the consumption of the output of other transactions is also same. And the third condition being that, the transaction which performs the final write operation on a data item Q should also be same. Right? So these three conditions, the way to remember them is that, for every data item Q, the same transaction should consume its initial value. Then second, whenever transactions are consuming the output of each other, those ordering should again be same in both S and S prime. And then finally, the transaction which performs the final write operation on any data item Q should also be same in both S and S prime. If all these three conditions are true in S and S prime, then we'll say that S and S prime are view equivalent. Right? So now how is view serializability defined? A schedule is said to be view serializable if it is view equivalent to a serial schedule. That is view serializability. Right? Remember that, every conflict serializable is also view serializable, but not other way around. Right? So this is an example. Right? So this schedule So this schedule over here, this is not conflict serializable because, of this part. So if you draw the that precedence graph which I was talking about, you'll have an edge from T27 to T28, and then you'll have another edge because of these two operations from T28 to T27, right? So in summary, this is not conflict serializable. But if you go ahead and match these operations against your view serializability conditions, this will sort of match the definition of view serializability, right? So quick thing to note is that every view serializable schedule which is not conflict serializable schedule has blind writes. So these are what are called as blind writes. So over here T27, it read the value of Q and then wrote the value of Q. But whereas T28 and T29, they just wrote the value of Q. So these are called as blind writes. Okay, so this is sort of a property that every view serializable schedule that is not conflict serializable has blind writes, right? So this was just to give you an idea of what other kind of serializabilities are there, right? So the summary statement being that whenever you are doing a TSO algorithm with Thomas Wright rule, which relaxes one condition, this condition of TSO is relaxed under Thomas Wright rule. Whenever you do this relaxation, you do not get conflict serializable schedules, but you get something called as view serializable schedules. Okay, I think I'll stop here. I think please go through these videos and the lecture slides, and let me know in case of doubts. You should also read the textbook, whatever reading material which has been posted for this concurrency control. The textbooks is quite well written. Okay.